Hello, welcome to today's class. And as the first slide indicates, today we will discuss X-ray diffraction by crystals and the very first and important law governing the X-ray diffraction by crystals, that is Bragg's law. In this way, whole lecture comprising two different subsections, one X-ray diffraction by crystals and another, that is Bragg's law. Let us discuss X-ray diffraction by crystals. We are familiar with diffraction of light that we have dealt in the section of optics and lasers in the previous year, and we have seen that diffraction of light is possible when we use a grating having thickness comparable to wavelength of the light. But what about diffraction of X-rays? X-rays are the electromagnetic radiations whose wavelength is in the range of 10 raised to minus 10 of meter, that is in the angstrom. Therefore, it is not possible to observe or to obtain the diffraction of X-rays by the simple optical grating. So, which device can be used for the diffraction of X-rays? In 1912, Max von Louis was first to show the path for X-ray diffraction of X-rays, and according to his suggestion, the single crystal or single crystalline solid can be used for diffraction of X-rays. The crystal or single crystal, as we know, consisting of the layers of atoms separated by a distance which is comparable to wavelength of X-rays, that is 10 raised to minus 10 of meter, and hence according to Louis there is possibility that X-ray can be diffracted with this much smaller thickness or this much smaller gap between the two layers of the single crystal. The experimentation on Louis' suggestion was performed by Frederick and Knipping. They demonstrated the diffraction of X-rays by thin single crystal of zinc blade, that is ZnS, and they obtained the X-ray diffraction pattern of zinc blade. And this X-ray diffraction pattern simply consisting of series of dark spots arranged in a definite order or arranged in a periodical order. One of the such type of pattern for silicon crystal is shown in this slide, and you will find that it is simply the arrangement of dark spots, regular periodical arrangement or regular periodical arrangement of dark spots or dark spots, series of dark spots in a definite order. Such type of pattern is called as Louis pattern, and it has been observed that it is showing periodicity of the crystal. Nowadays, X-ray diffraction by crystals is a very important tool, as it is used for the determination of single and polycrystalline structures, their parameters, lattice parameters for example, different parameters, structural parameters, and as well as the X-ray diffraction of crystal is an important tool to determine the wavelength of X-rays. Let us look at the next point. Today we will discuss very important one, and that is Bragg's law. Though Louis has suggested that X-rays can be diffracted by the single crystals, and Frederick and Knipping has demonstrated the diffraction of X-rays by single crystal, and they recorded the diffraction pattern of the by this X-ray diffraction by the single crystal, and that is simply the series of dark spots, and that we call it as a Louis pattern. But the theoretical background or a law, we can say, that is not yet derived, and these are the Bragg duo, father and son, that is W.H. Bragg and W.L. Bragg. In 1915, they derived a very simple diffraction model to regularize or to put the equation of diffraction of X-rays by the crystals. According to Bragg, the crystal is divided into sets of parallel planes. So as you know very well that a crystal consisting of regular arrangement of atoms or molecules, and these atoms or molecules are divided into different sets of planes having different Miller indices. Now, according to Bragg, the diffraction when the X-rays are incident upon the single crystal, the X-rays get diffracted simply as if they are reflected from these planes in the crystal. So, diffraction of X-rays by the crystals is equivalent to reflection of X-rays, and consequently diffraction and reflection are the interchangeable terms used by the Braggs as far as diffraction of X-rays by the crystal is concerned. Accordingly, they derive a simple mathematical relation that serves as a Bragg's reflection, condition for Bragg's reflection, and that is known as Bragg's law. Let us see the details of the Bragg's law. Now concentrate upon the figure shown in this slide. The figure shows Bragg's reflection of X-rays from the atomic planes of the crystal. As shown in figure, there are three atomic planes shown. The atomic planes are parallel to each other, having different Miller indices HKL. A parallel beam of X-rays of wavelength lambda is supposed to incident upon the crystal or parallel atomic planes of the crystal at an angle that is known as glancing angle theta, as shown in the figure. Such rays lie in the plane of the paper. It is considered that, as shown in the figure, the ray 1 and ray 2 lie in the plane of paper. Plane of paper is same as the plane of incidence. These two rays, ray 1 and ray 2, strike the upper two planes, first two planes as shown here. Ray 1 incident at point P, ray 2 incident at point Q. Both are incident at an angle of theta. From point P and point Q, the ray 1 and ray 2 get reflected and diffraction of X-ray took place. The reflected rays interfere with each other constructively. So, constructive interference of the reflected rays took place, and that gives rise to diffraction pattern of the X-rays by the crystal planes. Now, in order to derive the mathematical relation governing the law, let us draw the perpendiculars PL and PM on the ray 2 incident and reflected respectively, as it is indicated in the figure. From the symmetry of figure, we find that angle LPQ and angle MPQ are equal, and that is equal to theta. The path difference path difference between ray 1 and ray 2, that will be simply equal to Lm plus Lq. Lm plus Lq, because it is the simple way to find the path difference, not necessary to explain. So, path difference between ray 1 and ray 2 is Lq plus Qm. Now, this is Lq and this is Qm. Now, what is Lq? Lq is the side in front of theta. So, therefore, it is simply equal to sine of theta into the diagonal. In this case, the PQ will work as a diagonal, and PQ is simply the interplanar distance between the two upper planes, and that is considered to be equal to D. So, D into sine theta, that will be equal to LQ, and again D into sine theta, that is equal to MQ. So, what is path difference? LQ plus QM, that is equal to D sine theta plus D sine theta, that is equal to 2D sine theta. Now, due to constructive interference of the reflected rays ray 1 and ray 2, the diffraction pattern of X-rays diffracted by the crystal plane is observed. And what is condition for constructive interference? Condition for constructive interference is that the path difference must be equal to integral multiple of wavelength, and in this case wavelength is supposed to be lambda. And what is path difference? 2D sine theta, and this 2D sine theta must be equal to integral multiple of lambda. So, the condition for constructive interference, by implying condition for constructive interference, we find 2D sine theta equal to n lambda, where n is an integer, and this simple equation governs the diffraction or reflection of X-rays, and that is called as Bragg's law. Now, let us interpret this equation for further applications. From equation, it is clear that the diffraction is possible for the values d, lambda, n and theta, which satisfies Bragg's condition shown by the relation 2d sine theta equal to n lambda. What does it mean? It means for n equal to 0, now let us put here n equal to 0. So, you will find that 2d sine theta equal to 0, sine theta equal to 0, that means theta equal to 0. Thus, what does it mean by theta equal to 0? Theta equal to 0, reduce this theta and you will find that, reduce this theta and you will find that the reflected ray or diffracted ray is along the plane of the, along the plane of the crystal, and hence for theta equal to 0, we can confirm that there is no diffraction. Diffraction cannot be observed experimentally or practically for n equal to 0. And for increasing values of n, this value increases, sine theta increases, that means theta increases. And with the increasing values of n, we have different orders with increasing values of theta. Thus, for given values of d and n, higher order diffraction lines appear for higher values of theta. The diffraction lines in this way appear for n equal to 1, 2, 3, etc., etc. So, first order diffraction, second order diffraction, third order diffraction, etc., etc. It is observed that intensity of the diffracted lines or reflected lines decreases with increasing values of n and theta. But important to note that the highest possible order of diffraction is determined by the condition imposed by sine theta. And what is condition for sine theta? That sine theta never exceeds plus or minus 1 or never exceeds 1. So, sine theta should be less than equal to 1. Now, we can rearrange the equation for 2d sine theta equal to n lambda for sine theta as shown here. Sine theta equal to n lambda upon 2d. That is, sine theta must be less than equal to 1, that means this must be less than, so n lambda upon 2d must be less than equal to 1. Okay. So consequently, it points that lambda must be less than equal to d. What does it mean? It means wavelength of the X-ray must be less than or equal to interplanar spacing of the crystal. For example, if interplanar spacing of the crystal is 10 raised to minus 10 of meter, or what we call it as 1 angstrom, then the wavelength, the X-ray must have a wavelength less than equal to 1 angstrom. This is the important condition, okay, to diffraction to occur. In this way, X-rays having wavelength within the range of 1 angstrom must be preferred for the crystal analysis. Then and then only the Bragg's condition satisfies and diffraction can be observed. With this, we conclude today's lecture and we'll stop. Thank you. Thank you for your cooperation.